Find the maximum shear stress in the steel in newtons per meter squared. In this problem, a cylindrical shaft is fixed to a wall at one end and free at the other end. The shaft is 2.5 meters long and experiences a torque at the free end of 4,000 Newton meters. The cross-section of the shaft shows the inside is composed of steel and the outside is composed of aluminum. And the diameters and shear moduli are provided. The shear stress in a cylinder in newtons per meter squared caused by torsion equals the torque applied to the cylinder in Newton meters times the radius in meters for the point being evaluated divided by the polar moment of inertia in meters to the fourth. To find the maximum shear stress in the steel, we must evaluate this equation using the torque, radius, and polar moment of inertia specific to the steel part of the shaft. We'll begin by calculating the torque resisted by the steel part of the shaft. In static equilibrium, the torque applied to the shaft equals the torque resisted by the shaft material, where the torque applied equals 4,000 Newton meters. The angle of twist in a cylinder, gamma, in radians, caused by a torque equals the torque, T, times the length of the shaft, L, divided by the polar moment of inertia, J, and the shear modulus, G. If we solve for the torque term, the torque equals gamma times J times G divided by L. Therefore, we can find the torque resisted by the steel by using the polar moment of inertia and the shear modulus specific to the steel. And we can find the torque in the aluminum by using the parameters specific to the aluminum. Notice for both these equations, the angle of twist and shaft length are the same for both materials. To find the torque in the steel, we'll first solve for the angle of twist, gamma, and then use that value of gamma to solve for the torque in the steel. So far, we already know the applied torque is 4,000 Newton meters. And we've been given that the length is 2.5 meters and the moduli of shear equal 7.7 times 10 to the 10th Newton per meter squared and 2.7 times 10 to the 10th Newton per meter squared for the steel and aluminum, respectively. But we still need to calculate the polar moments of inertia. The polar moment of inertia for a circular cross-section equals pi divided by 32 times the diameter raised to the fourth power. The problem statement provided diameter 1 and diameter 2 as 0.054 meters and 0.072 meters. Plugging in 0.054 meters in for D, the polar moment of inertia for the steel equals 8.348 times 10 to the negative 7th meters to the fourth. The polar moment of inertia for the aluminum equals the difference between the polar moment of the larger diameter and the polar moment of the smaller diameter. After plugging in the values for D1 and D2, the polar moment of inertia for the aluminum equals 1.804 times 10 to the negative 6th meters to the fourth. Having solved for the polar moments of inertia, we can plug those values into our equation, and gamma, the angle of twist, equals 0.0885 radians. This value for gamma is plugged back into the equation for torque resisted by the steel material, and the torque resisted by the steel equals 2,276 Newton meters. Returning to our initial equation for the maximum shear stress resisted by the steel material, we can plug in the values for the torque resisted by the steel, the radius of the steel, and the polar moment of inertia of the steel. And the maximum shear stress in the steel computes to 7.361 times 10 to the 7th newtons per meter squared. When reviewing the possible solutions, the answer is D.